Hello student, welcome to our web optics course. Today we have lecture number 41 and in this lecture we will going to discuss about the Fraunhofer diffraction for a circular aperture. So we have lecture number 41 today. I am going to discuss about what is the Fraunhofer diffraction pattern for a circular aperture. So far we are dealing with a slit whose width is small compared to the length, but now we are going to discuss about if instead of having a slit, a narrow window, if I have a aperture, a circular aperture, what should be the distribution due to the Fraunhofer distribution of the intensity due to the Fraunhofer diffraction. So first let me draw the aperture here. So we have a hole here, circular hole. Try to draw in 3D. So this is the circular hole we are having. Let us put the x and y axis also. This is x, and this is y. So I have a screen here. Having x and y coordinate as well. So I want to find out something over here. So this is a point P. What is the field distribution at point P when we have aperture like this? So I join this P here and I take a small section here over y. I shade this section and then I draw a line from this section to the point P. So this is the point P where two lines are coming, two rays are coming, and if I draw a perpendicular here, so this is from over here, this is y, this is dy, a small section. So here I am drawing in a magnified version of this. So I have the circular aperture This is my x coordinate, this is my y coordinate, and I have over a distance y, I have a strip here. Small strip. So, this is my y, and this portion is dy, and if I draw a line here, so that is my x, big X, say. Okay, and the radius is r. So, I am just drawing the geometry here. This is the center. So, this is the geometry we are having, and now we are going to utilize this. So, first what we need to do is to find out what is the electric field at point P due to this small strip, this small area that is drawn over the length y, this dy. So, dE at point P, this is a small field, that is the field at P due to the small strip. Here also I magnify this figure. Now, dE essentially the electric field that is coming from this is essentially a circular wave that is coming, a circular a spherical wavefront that is coming, and I write this spherical wavefront in the form, or the spherical wave in the form like this. That is the propagating part, but also we know that when the waves are moving, then all the waves are moving, but they are not in the same phase. So, when we have this strip over this strip, there will be an additional phase compared to the point that is coming from this origin, the electric field that is coming from this origin. So, there will be a path difference between these two. I draw that path difference, and due to this path difference, that leads to a additional phase that we need to encounter, and over the area dA. So, delta here, so electric field, this is the intensity of the electric field per length, and then this equation satisfying, this equation suggests that this is the total electric field due to this strip. So, delta is a phase difference and that is due to the path difference. So, that means we have k multiplied by the path difference and what is the path difference? Let me draw this part again here. It is like this. So, I have origin here and this is the strip, this is y, and this is the point, say P, some point P, suppose this is the point P. So, I join this to line, and if I draw a perpendicular here, then that is the path difference we are having. And if it is y and if this angle is theta, then this path difference delta will be y of sin theta, that we already calculated earlier. So, that path difference will be y of sin theta. So, here I write it, it is k and y of sin theta. What is k? K is a propagation constant and it is written as 2 pi divided by the wavelength that is used in this experiment. Okay. So, this is the overall structure I try to draw here, and now we are going to calculate. So, in the calculation is nothing, we just need to integrate to find out total field over area, and that is the tricky part. So, dA, so let me write down once again, dEP, what we find is E naught divided by R naught, because it is a spherical wave that it should come out from this aperture. So, I need to take account that form. That was the form. And let me draw once again here quickly. Here this was the strip and we have y here, and that was r, that is x, and that is y, and this is the strip we are talking about. This is the strip we are talking about. So, dA, I first need to calculate what is the area. Area dA is the strip area, and that is x multiplied by dy. What is x? X is this length. You may remember that I defined this as big X. From here to here, this length I write x, and there is a relationship between. So, let me write down what is this is 2 of x by 2, because from here to here this coordinate is x. So, this is small x by 2 multiplied by dy. Also note y square plus this length, that is x by 2 whole square, is r square. So, x by 2 is simply root over of r square minus y square. That is the relationship we already have. So, that relationship if I put here in the expression of dA, then everything will be in terms of one variable, and that variable is y, that we want, because in the delta, mind it, delta was k y sin theta. So, the variable here is y, because k is constant and we are looking for a particular angle theta. So, dA is essentially 2 of x by y is nothing but root over of r square minus y square and dy. that is the area we are having. Now, once we have the area in form of y and dy, then we are in a position to integrate. So, the total field now due to the entire aperture will be the integration of the field that we are having, small field that we are having over this area dA, and I am going to integrate over area. So, that gives me E naught divided by R 0 e to the power of I k R naught minus omega t, where R naught is the distance from the center to center. Center to center means I am talking about this distance from here to here, this is R naught, and then I integrate, and this we will have e to the power I delta, which is I k y sin theta, and then we have 2 of root of r square minus y square and dy. Okay. And then that integration over dy means I need to go, now the y can go from 0 to r and 0 to minus r. So, eventually it goes from minus r to plus r. So, this integral if I write here, then it should be 2 of E naught divided by R naught e to the power of I k R naught minus omega t, and then I have integration, and this integration goes minus r to r and e to the power of I k y sin theta and root over of r square minus y square dy. So, important thing is to do this integral, and that we will going to use with a trick, knowing something. So, let us take a variable nu as y by r. So, d nu will be 1 by r dy. If y tends to r, then plus minus r rather, then nu tends to plus minus 1. So, the integral will change. So, let me write down this integral once again. So, E p with this change coordinate will the initial term, which is 2 E naught divided by r 0 e to the power of I k r 0 minus omega t, and then we have integration minus 1 to 1, and then we have e to the power of I y by r, I put gamma. So, I write it as gamma alpha, and then I have r, if I take common, r root over of 1 minus nu square, and then dr is this quantity. So, dy is r into d nu. Okay. When my my alpha is, so what was there, so let me write down here in the previous equation what was there, it is e to the power of I k y e to the power I k y then sin theta. So, if I go back and write, it was e to the power of I k y sin theta, that was the term, and then root over of r square minus y square term. So, from here if I take r square common, then this r is coming out, then in the root we have 1 minus y square divided by r square, which is nu square, because y by r is nu. Here in the in the power of e, if I write e to the power of I k nu, then 1 r should be there. So, this term actually it is written e to the power of I k divided by r, then we have r, and then we have y, and then we have sin theta. So, y by r I can write nu. So, then it should be e to the power of I k then r sin theta multiplied by nu. Okay. So, that means alpha here is k r sin theta. So, alpha is k of r k multiplied by r sin theta, that is my alpha. So, I can take this r outside and another r is there. So, my EP is essentially 2 of E naught divided by r naught multiplied by r square, then e to the power of I k r naught minus omega t. Then we have an interesting integral, integral minus I minus 1 to plus 1 e to the power of I nu alpha root over of 1 minus nu square d nu. So, I put some emphasis here in this integral because it is not possible unless you know what is the value of the integral. There is identity, I am writing this identity in a different color maybe, and this identity is this. So, minus 1 to plus 1 e to the power I nu alpha root over of 1 minus nu square d nu is something equivalent to pi divided by alpha and the Bessel function of first kind J1 alpha. This is an identity and this is a very important identity. So, I suggest the student to remember that in order to do this problem we have to utilize this identity, otherwise we can't execute this integral, and based on this identity the result will come. Okay. So, now once we know what is the value of the integral, then we are in a position to find it, but before that I like to show something about this. So, J1, this is the Bessel function with the first order Bessel function, and that is equal to, if I, this is a series function, we know the Bessel function is a series function, and I believe the students that when you derive this you should have an understanding of the Bessel function. Maybe in your mathematical physics course you already learned about that Bessel function. this is a specific differential equations is there, and Bessel functions are the solution, series solution of this specific integral, and that I like to expand here this series, whatever the series we are talking about. So, Bessel functions J1 alpha is a series, and it will be defined this alpha by 2 cube divided by 1 square multiplied by 2 alternative plus alpha by 2 to the power 5 divided by 1 square into 2 square into 3 and so on. There will be this will be alternative plus minus sign. So, this term minus, this will be a minus sign here and so on. So, this is the expansion of the Bessel function, and note that J1 alpha divided by alpha, this is half minus this is alpha by alpha square by 2 cube, in the denominator I have 1 square 2 and so on. If that is the case, then that limit will be there. So, when limit alpha tends to 0, then for that limit J1 alpha divided by alpha is equal to half. Okay. So, that is the limit we have, because that. So, when we plot J1, that is the first this Bessel function of these things, then it goes from 0 actually. So, there is a, so if I plot this, it will be like this. So, this is the form of the Bessel function. When we plot J1 alpha, mind it, I am plotting J1 alpha, not J1 alpha divided by alpha. So, that is 0. This point, the first cutting point is 1.22 pi. This I plot as a function of alpha. This point is 2.22 pi. This point is 3.23 pi and so on. These are the cutting points. It is important that we should note about the cutting point. Here we have a 0, here we have a 0. So, these are the cutting points for this Bessel function of first kind. Now, let me go back to the field calculation. So, what was there? So, EP then essentially 2 of r square E naught divided by r naught e to the power of I k r naught minus omega t, and then we have pi, then J1 alpha, then divided by alpha, because that was the value of the integral we calculated. Now, what is the intensity? The intensity IP will be proportional to the field amplitude mod square. If that is the case, I can write down IP in a very standard form, and that is I naught and J1 alpha divided by alpha whole square. Mind it, alpha here was r k naught sin theta. It is also written as r is the radius of the circular aperture, if you may remember that was our r. So, I can write it as half of d in terms of diameter, then k naught or k whatever, k sin theta. I did not use k naught, so better I remove this. So, d is the diameter of this stuff. Now, if I want to plot that, then how the plot will look like, let us quickly understand. So, this is the field distribution we are having. So, if you plot the field distribution here, it will be like this. Like we get for the single slit, but the functional form is different. Mind it, here we are plotting I p, which is proportional to this quantity J1 alpha divided by alpha whole square of that. And note, when alpha tends to 0, this is alpha, we show that when alpha tends to 0, J1 alpha divided by alpha is not equal to 0, it is going to the value of half, that is the limit. So, that means we get a maxima here. This is the point where J1 is vanishing, and we know where the J1 is vanishing. We show that it is 1.22 pi, this is 2.22 pi, and it is 3 point around 24 pi, something like this. These are the points where we have minima. So, this is the distribution of the intensity where the principal maxima occurs when alpha tends to 0. So, this is where alpha is 0, and alpha is 0 means from here we can see that when theta is 0. So, theta is 0 tends to 0 where we have a principal maxima. So, in 2D how the figure will look like, because the spectral will be 2D. So, there will be a pi symmetry here. So, the spectral, if I draw that, it should be like this. So, I have a maxima here, then minima, then I have a maxima here, then I have a maxima here. So, it will be like a concentric circle like we have in our other light experiments. And how this plot is consistent here. So, I have a maxima here, and if I go, then there is a minima, then there is a maxima, then there is a minima, then the maxima, then there is a minima, and so on. So, this is exactly following this plot whatever we had here, these two plots we are talking about. So, I just discuss about that how these two plots can be one can have. So, quickly we whatever the time left, let me continue, because this is associated with that, that where is the these secondary maxima, the condition of the secondary maxima, etc. So, the secondary maxima we have this secondary maxima or the secondary minima, better you just okay, secondary, first we calculate secondary maxima. So, secondary maxima one can have when d alpha of this quantity is 0. So, that is a difficult calculation. Using the computer you can do that, and if you do, you will find that when alpha, the value of alpha is 1.635 pi, then we have a secondary maxima. When alpha equal to first secondary maxima, then when alpha equal to 2.679 pi, then we have a secondary maxima, and so on. First etc. And the minima we have already discussed, and let me define that. So, secondary minima so let me draw the structure here side by side, the spectra, that it is like this. So, this point and this point are first and secondary maxima. So, this is 1.635 pi and this point is 2.679 pi. These two we have, and this we know where J1 is 0. So, that we already calculated. So, J1 alpha, that is 0 obviously when alpha not equal to 0, that is the condition. So, first minima is around 1.22 pi, that is here 1.22 pi, that is the value of the alpha for which I have a first minima. So, let us understand that what is. So, alpha, that is equal to alpha, and alpha is how much? Alpha is d by 2, then k, which is 2 pi divided by lambda, and the angle for sine, say sine theta 1, the angular. So, that is the first minima, and that is 1.22 pi. If that is the case, we can have sine theta 1 is equal to 1.22 divided by d pi, that is the important expression. So, which angle we are talking about is this. So, I have this circular aperture, and for that I am having this spectra which looks very close to the spectra that we have for single slit, and this is the theta, this is a theta 1 for which I am getting the minima. So, this calculation suggests that sine of theta 1 is equal to 1.22 pi divided by d. If d is small, that is the radius, that is the diameter of the small, this will go to shift to the other limits, to more wide. So, I have one aperture with the small d, then this spectra will be more spreaded. It should be like this. So, this theta 1 prime will be larger than this one because the d is smaller here. because the d is smaller here. So, with that note I like to conclude because I do not have the time. So, today what we discuss is the diffraction pattern generated due to circular aperture, very important. Normally we have a circular aperture, normally we have a slit, but if somebody do the experiment with the circular aperture, Fraunhofer experiment, he or she can find a intensity pattern that we derived today, and it deals with the Bessel function, and the Bessel function of the first order Bessel function of the first kind, and then we find that how it distribute and what is the location of principal maxima, secondary maxima and all, and also the location of the minima. And we find that if the d value is less, then the spectra or whatever the structure we have is get broadened. So, with that note I conclude here. Thank you very much for attention and see you in the next class for more.